Hello dear learners, I'm Zinnah, a chemistry teacher. Today I'm with Iodometric titration. In this titration you get two solutions. One is solution of iodine with unknown concentration. Another is solution of thiosulfate with known concentration. This is also called standard solution. In the reaction between iodine and thiosulfate, you will get iodine gains electrons and is reduced. And here iodine is also called oxidizing agent. And on the other hand, thiosulfate loses electrons and is oxidized. And this is also called a reducing agent. You may combine the oxidation equation of thiosulfate and reduction reaction of iodine together to develop the redox equation. And in the developed redox equation you get the stoichiometry, mole ratio of iodine to thiosulfate is 1:2. Using the mole ratio and the volumes of the solutions which we get after the titration, we can estimate concentration of iodine. For the titration, first pipette out certain volume, suppose 25 cm cube of the iodine solution into a conical flask and the thiosulfate in a burette. And before you start adding thiosulfate to the conical flask, you just notice and record the initial burette reading of the thiosulfate and then run the solution to the conical flask until the color changes. The conical flask contains iodine, which is a brown solution, and when thiosulfate runs into the iodine and redox reaction takes place producing persulfate and iodide, both are colorless solutions. So when the reaction is complete, then you will get the solution turns colorless. And when the solution turns colorless, you stop adding the thiosulfate and record the final burette reading. And then subtracting initial burette reading from the final burette reading, you can get the titer. The volume has been added to neutralize or to react with all the iodine. And this is how you can easily get the volume of iodine and volume of thiosulfate. You certainly know that for the reliability you need to carry out the same titration several times so that you get concordant value which should be averaged to get the mean titer. And when the titration is complete, what you have now, you have the volume of iodine, which is maybe 25 cm cube, and volume of thiosulfate that you are getting from the burette. And then you calculate mole of the thiosulfate, which is a standard solution. Here thiosulfate is with known concentration and its volume is also known in the titration. The mole can be calculated as mole equals volume into concentration, so you get mole of the thiosulfate solution. And from the mole of thiosulfate solution, using the stoichiometry, you can estimate mole of the iodine. You already got that iodine is half of the thiosulfate in the reaction. So divide mole of thiosulfate with 2 and you get mole of iodine. This is how you get mole of iodine. And now divide the mole with volume of iodine, which may be 25 cm cube, and this should be in dm cube. And eventually you get the concentration of iodine. In this titration, we just have one challenge, which is to find or determine the end point of the titration. Iodine is colorful substance, which is brown, and brown when the reacts away, then you get colorless solution. But the color changes is not very sharp because iodine is brown, and when you add thiosulfate gradually, then its amount decreases. So when the amount of iodine decreases, its color, intensity of color also decreases gradually. So the brown solution turns orange, then pale yellow or straw color, and then eventually turns colorless. So end point is difficult to be determined. One thing you can adopt to solve this problem, which is using an indicator, which is stars indicator. Stars is an indicator which combines with even a small amount of iodine to form a blue-black solution. But here's one more concern of using the stars indicator, because the stars itself may consume some iodine. So what we do, we just use the stars at the middle or at the end of the titration, which means you just take the iodine solution in the conical flask and thiosulfate in the burette and run the thiosulfate into the conical flask till the color fades away. When the color fades away, then you add few drops of starch solution into the conical flask. Then you will get, suddenly the color will change into blue-black. Now you add more thiosulfate, and when all the iodine with the starch reacts away, then the color will turn colorless. Then you stop adding thiosulfate, and this is how your problem could be solved. But if you add starch at the beginning of the titration, then the starch get large concentration of iodine, which is at the beginning. Then starch itself consumes some iodine and forms a solid complex. Then not all the iodine will react with the thiosulfate, and this will cause a major error in the titration. This is how you may estimate the concentration of iodine by titrating with the standard thiosulfate solution. So after we understand the concept of iodometric titration properly, we can use this concept to estimate concentration or mole of some other oxidizing agent. Oxidizing agent means with gains electrons, and you already got thiosulfate which loses electrons, so you can establish another redox reaction with a new oxidizing agent with thiosulfate. But you may not be able to have a titration again, because for the titration you need to have the color changes. Suppose I'm giving you an example. Chlorate 1 here. Chlorate 1 gains electron in presence of acid to form chloride ion. So here this is an oxidizing agent, and this is reduced. And if you take this chlorate ion or chlorate solution in conical flask and titrate against thiosulfate, yes, that will be a redox reaction, but you cannot estimate the end point of the reaction because no color changes. Using help of iodine or the concept of iodometric titration, you still can estimate the mole of chlorate or concentration of chlorate ion. How is that? And for this, take certain volume of chlorate. Suppose you get 25 cm cube chlorate solution is pipetted out into a conical flask and add excess sulfuric acid to the conical flask. Now add excess potassium iodide. Look, we are getting help of potassium iodide, and here will be a redox reaction in the conical flask where you will get iodide will oxidize to iodine and chlorate will reduce to chloride. And as you are using their excess sulfuric acid and excess potassium iodide, so product here, which is iodine, will depend on the limiting reactant, which is here chlorate 1. And after the reaction is finished, you have now certain amount of iodine in the conical flask. Now place the conical flask containing iodine under a burette which is already full with thiosulfate solution, and add thiosulfate solution to the conical flask. Here the thiosulfate will run to the conical flask and will react with the iodine, and here we'll get iodine will reduce, iodine will gain electrons to form iodide, and when all the iodine will react away, then you will get all iodide. No iodine will be there, then the solution will turn colorless again. As you already got there, the amount of iodine reduces gradually for the reaction with thiosulfate, so the color will change gradually, so it's difficult to estimate the endpoint. Again, you can use here the stars to solve the problem. Now add the required amount of thiosulfate into the conical flask again till the color changes to colorless solution. Now when solution turns colorless, then stop adding the thiosulfate solution and record the final burette reading. And subtracting the initial burette reading from the final burette reading, you get the what volume of thiosulfate has been required to react with all the iodine, which was formed previously by reacting iodide with the chlorate ion. And when the reaction is complete, you certainly need to repeat the titration several times for the reliability. And when you get few concordant result, then from the concordant result you average to get the titer. Now the calculation, our goal was to estimate the concentration or mole of the chlorate ion, and here you first need to estimate or calculate mole of the thiosulfate, because thiosulfate is again here standard solution with known concentration. Its volume is known after the titration. You estimate mole of the thiosulfate, and from the mole of thiosulfate you get mole of iodine. How do you get this? Just divide with 2, you get mole of iodine, which was produced when you have mixed iodide and chlorate. And from the mole of iodine you can estimate mole of the chlorate ion. In that reaction you got the mole ratio 1:1, and so the mole of iodine is same as mole of chlorate. So ultimately from the mole of thiosulfate you get mole of iodine, and then from the mole of iodine you get mole of chlorate ion, and you can estimate mass of chlorate or concentration of chlorate. If you look at the consequences, you add their potassium iodide, which is iodide ion. Iodide ion reacts with the oxidizing agent chlorate to form iodine, and again iodine reacts with the thiosulfate, and the iodine again reverted into iodide. So you're starting with iodide, which forms iodine and again forms iodide. So we call this reaction as a back titration, because iodide is back. So this is how you can estimate concentration or mole of chlorate here, and instead of chlorate you can have any other oxidizing agent to react with potassium iodide in acid medium if required, and to form iodine, and again titrate the iodine with thiosulfate, and you can estimate mole and amount of the oxidizing agent in the similar way. So I hope this has made your concept of the iodometric titration and the back titration very simple, and I'm giving you some example here. If you exercise the examples, this will be very easy and simple for you. Thank you very much.